Hello friends, welcome back again to Math 135. Today we are covering section 2.3, which is about dividing polynomials and the rational zero test. So those two topics. So today we learn about dividing them. Yeah, okay, that's what I just said. Okay, let's look at what we're doing. Number one, how to use the division algorithm specifically for polynomials, but along the way you'll see it's basically the same as the normal division algorithm for numbers. Number two, how to use the remainder and factor theorems. And then number three, how to use the rational zeros test. I wrote zeros here, and I think it's actually zero test, but yeah, same thing. You're finding zeros that are rational numbers. Okay, number one, use the division algorithm for polynomials. We're going to start things a little differently from normal. We're not going to talk about any theory yet. We're just going to jump straight to the questions. So we're going straight to the questions, and then we'll come back to those, okay? Okay, what are the questions? 1 through 3. Question 1 through 3 is just division questions. And you notice this already prepared here because I'm reshooting this for the third time. The first time I recorded vertically like an idiot and not remembering that that cuts off the video from YouTube. And the second time I just had a typo and it's like, yeah, mess up. Anyways, let's go. Number one, when you're dividing something, just quick terminology. This guy being divided, we call it the dividend. And this guy dividing, we call the divisor. And the way I used to get those mixed up all the time because they kind of sound similar. The way I remember now is the guy that's taking the action, his name sounds like he's taking an action. He's the divisor, kind of like the Terminator or the Exterminator, the Destructor or whatever it is. He's doing the thing, right? So he's dividing. Okay, so the other guy being divided, he goes inside the division symbol. The divisor always goes outside. And then you know the drill, right? You go, okay, how many times does 3 go into 7? The answer is 2. And then you multiply those together, and the result of that multiplication goes here, and you're subtracting it. So 7 minus 6, the answer is 1. And then that becomes the remainder, because there's nothing else left. Now, notice a couple things here. 7 is equal to that original divisor times the quotient, right? Or the quotient times the divisor. I forget which way you're typically writing, but it's the same either way. So it's the quotient times the divisor plus the remainder, right? Or equivalently, you could say the result of 7 divided by 3 is the quotient. Quotient is 2 plus the remainder divided by the original divisor plus 1 over a third. 7 thirds is equal to 2 and a third. Or you can say 7 is equal to 3 times 2 plus 1, right? That's how division works. The algorithm, the algorithm is just a series of steps to reach a solution or end result. So that algorithm gives you the quotient and it gives you the remainder. Yeah. Okay, let's try the same thing with number 2. This time, bigger number is 41, goes inside, divisor out here by, that's 2. 2 goes into 4 2 times, multiply those two numbers together, and you subtract. So 4 minus 4 is 0. This number comes down, right? And you say, okay, 2 goes into 1 0 times, so this time you fill in the 0 there. I don't like the way that looks with different colors. I'm going to leave that here, like that. Okay, and then after that, you can't go in there again, so that the rest is just the remainder. Remainder is 1. Yeah. Now, again, notice, I could say 41 is equal to the divisor times the quotient plus the remainder, in this case, 1. Or I could say 41 divided by the divisor of 2 is the quotient plus the remainder divided by the divisor. Yeah, see that? 41 divided by 2 is 20 and a half. Or 41 is equal to 2 times 20 plus 1. Okay, one more, and same thing, right? And, you know, the point of this, guys, I know we're just doing long division. You're like, yeah, I know how to do long division. I remember when I was a kid, I forgot how to do long division over the summer. Like, I learned it, and over summer went by, and then school came around, I didn't know, and then parents were a little irritated with me, but it's okay. They were pretty cool for the most part. Okay, 25, 4, 5, 9, divided by 23. 23 goes into 54 2 times. Notice I'm just looking at the minimal part I can look at that will fit into. And then 2 times 23 is 46. 54 minus 46 is 8. And then next step, you bring down the next digit, right? Bringing that guy down. 23 equals to 85 3 times. And 23 times 3 is 69. 85 minus 69 is 16. And then you bring the next guy down. 169. And 23 equals to that. Either 5, 6, 7 times. 5 times to get up to 100. 2 more times to get closer. Actually 5 times 60 past 100. And you can, if you that was my initial guess. If you are higher or low, you can just check by multiplying, right? 7 times 3 is going to be 21. 7 times 2 is 14 plus 2 more is 161. So that's 161, right? The product of, product of that guy and that guy. And then you subtract it, right? You subtract it. So it's 169 minus 161, it's just 8. That makes it the remainder. The same deal here. You could say, if you wanted to, 5459 is 23 times 237 plus the 8. Or you could say 5459 divided by the divisor is the quotient plus the remainder divided by that same divisor. So check that out, right? That's what the division algorithm is all about. Okay, let's go back to our notes here. And this is all just saying the same thing we just talked about just now through the examples, right? If you divide a number A by a number D, by one number by another number, you get the quotient with the remainder, right? Where that original number is the quotient times the divisor plus the remainder. So for example, 41 is 2 times 20 plus 1. And note here, the remainder has to be less than the original divisor, because if it wasn't, that means that you could have increased the size of the quotient, right? So remainder should always be less than the divisor. Now, equivalently, you could say A divided by D, so the dividend divided by the divisor is the quotient plus the remainder over the divisor. That's like saying 41 divided by 2 is 20 plus a half. Yeah. Okay, before you discuss the next part, we're going to go straight to question number 4. Let's talk about question number 4. And what you're going to see is with question number 4, which is now we're moving on to polynomial division, you're going to see that it's really the same thing all over again. It's the same. It's basically the same thing as normal long division. You see my work where I did it previously because I had to shoot this more than once. Okay, so we're taking the dividend, right? And it goes in the same spot. Just copying it down here. Oh, actually not copying out exactly because see this? I go from x squared to 18. I'm missing an x term. So anytime you're missing a term, you just leave a placeholder for it. You can write 0x or you can just write 0. And the reason for that is the same reason as like you wouldn't write 19 if you wanted 109. You'd have to have that 0 to indicate a placeholder for that digit, right? So same reasoning here. I'm having the 0x to be a placeholder for the x column. So anything that happens with x fourths, I think of happening within that column. This is the x cubed column, the x squared column, the x column. This is the constant number column. So I want to keep everything lined up when you do your division, just like how you would when you do your division with numbers. You line up the hundreds place, the thousands place, the ones place, etc., right? Okay, the divisor goes outside there, right there. Yeah, I didn't give myself space to write the answer, so let me move that down. Okay, and then the process very similar. So what I'm looking for is aside from this side, where does this x fit into that? Yeah, and I say that really weirdly. When I do this division, I just focus on the leading terms. So in this case, the leading term would be the x. And here, the leading term would be the 2x to the 4th. And I say to myself, okay, how many times does this leading term go into that leading term? The answer here would be 2x to the 3rd, right? And that's an x to the 3rd, so it goes over this x to the 3rd column here. And then you remember from long division we just did? What's the next step? You take this number that you put, or this term, you multiply it, and then you subtract the result right over here, right? So that's exactly what I'm going to do. I'm going to say 2x to the 3rd times x minus 2 is 2x to the 4th. And 2x cubed minus 2 times negative 2 is negative 4x to the 3rd. Now, big suggestion here. When you take the result of those things multiplied together, put it in parentheses and then subtract outside. And this is just going to help you to keep your signs correct. Okay. So then those guys cancel. I've got x cubed minus a negative, which means x cubed plus, which means it's going to be plus 5x cubed. And then just like with normal division, you're going to bring the next piece down. Okay, now I'm looking, how many times does x, really just this part, x go into 5x cubed? The answer is 5x squared times. Okay, what's the result of multiplying 5x squared times x minus 2? It's going to be 5x cubed minus 10x squared. Okay, again, parentheses there, and subtract. These guys cancel. I've got negative 16x squared minus a negative, which is plus, which means the same thing as plus. And that's going to be plus 6. Negative 6x squared, yeah? Negative 16 plus 10 is negative 6. Bring that 0 down next. So plus 0. Or 0x if you like. And then now, same question. How many times does x go to 6x squared? The answer is, this is negative, yeah? So negative 6x times. Now I'll multiply negative 6 times x minus 2. I get negative 6x squared. Negative times negative is positive, so plus 12x. And then, I want to do new color. Good. And then you're gonna subtract that whole result. The whole result. So again, keep the parentheses there, yeah? Cancel, cancel. And then 0 minus 12x is negative 12x. Finally bring the 18 down. So that's plus 18. And same deal. How many times is x going to negative 12x? And this time, the answer is just a number. The number is negative 12. So I take negative 12 times negative, I'm saying negative 12 times x is negative 12x. Negative 12 times negative 2 is positive 24. And remember, I'm subtracting that whole result. That whole result. Okay, negative 12x minus negative 12x is going to cancel out. I've got 18 minus 24 now, which is negative 6. And that is the last thing. X cannot go into 6, so the remainder is negative 6. Okay, there's your answer. So I just ran the division algorithm for polynomials, right? And what does it mean? It means if I take my original dividend, 2x to the fourth plus x cubed minus 16x squared plus 18, that's equal to my divisor times the quotient, 2x cubed plus 5x squared minus 6x minus 12, plus the remainder, of this case, negative 6. Yeah. Or, so that's the one formulation, right? Or I could also say my original dividend, thing that's being divided, over the divisor is equal to that quotient, 2x cubed plus 5x squared minus 6x minus 12, plus the remainder, in this case negative 6, over that original divisor again, divisor. All right, let's go back to the theory now. What did we just do? Or what did we just see? We saw the division algorithm for polynomials. That process of running those steps to divide is called the division algorithm. And the division algorithm says if you do this process and you divide your f of x, the original polynomial, by some divisor polynomial, you'll get a unique quotient and a remainder where that original value is equal to the divisor times the quotient plus the remainder. And that's what we saw, right? The original guy was equal to the quotient, or I mixed up the order here, but quotient times divisor plus the remainder. Yeah. Now here, in the normal numbers, remainder had to be smaller than the divisor, right? In this case, the remainder has to have less degree than the divisor, smaller degree. Because otherwise, if it didn't have a smaller degree, then that would have meant that you could have changed the q of x, right? You could have made the q of x a little larger. Okay, equivalently, you can also say fx over d of x is the quotient plus the remainder over the divisor. That's like saying what we said earlier, right? Take that number divided by the divisor, it's the quotient plus the remainder over the divisor. Okay, one last thing to cover in this video here, which is synthetic division. Synthetic division, this only works, well, I guess technically you can use it in other circumstances, but the way we typically use it is only when you have the divisor of the form x minus c. Here I wrote x plus c as well, but really x plus c, you can think of x plus c as really just x minus a negative c. So in that sense, you can really convert it just to x minus something, minus some number. Yeah. Okay, when you have something like that, you run synthetic division. If you want to see synthetic division taught by someone else, there's a whole bunch of good videos on YouTube, or just Google search, you'll come all kinds of stuff. Oh, where am I omitting? But what I want to do now is we're going to repeat the same exact question. This is question number 5 actually. We're doing the same numbers, same polynomials, but we're going to do it this time using synthetic division. So let me show you the process of synthetic division. And all a synthetic division is it runs the division algorithm in the special case that your divisor is something with just an x in the front. Notice that the divisor is just the term for the leading term is just x. There's no coefficient like 2, there's no 3, and there's no square, there's no cube, nothing like that. It's just a regular old x in the front. This is when you can use it, yeah? And what do? Okay. So I'm looking for something with x minus c, and what I want to identify is what is that c? What is c? In this case, c is going to be 2. So the first step is to identify that, and then you write it in a little box here. So here c is 2. Next step, second step, write your coefficients of the polynomial here. So it'll be 2 for 2x to the fourth, 1 for x cubed, negative 16 for negative 16 x squared. There's no x term, so just like we did with the other division, I'm going to leave a placeholder. This time the placeholder is just 0, and then the constant term is 18. Yeah. Then you give yourself a space, and then you draw a line underneath here. And then here's where we run the algorithm. Okay, ready? First step. You bring this number straight down. That's going to be your leading term. Always leading term is going to be that number because that's how many times x is going to fit into 2x to the fourth, right? So that number comes straight down. Okay. And then here's the next step you're going to do. You're going to multiply what's in the box times the number down here. Multiply them together, and you just input that in this spot here. So in this case, 2 times 2 would be 4. And then you just add down. 1 plus 4 is 5. And you repeat over and over again. So 5 times 2 is 10. And you add negative 16 plus 10 is negative 6. Negative 6 times 2 is negative 12. And add 0 plus negative 12 is negative 12. Negative 12 times 2, negative 24. And you add, that's negative 6. Okay, so always this number here is going to be the remainder. And because you're dividing by something with just an x and the remainder has to have a lower degree, that means it's always going to be just a constant. So the remainder is the constant here. And this guy, this is going to be your polynomial. So this is your constant term, x squared term, x cubed term in that order. So that means your result, the quotient is going to be 2x to the third plus 5x squared minus 6x minus 12. And then the remainder is negative 6. And check this out, guys. Does this look familiar to you? This thing? Well, it should, because we did the same question the long way earlier, right? And we got the same answer. So synthetic division, if it applies, and it applies as long as you have something of the form x minus a number as your divisor, then it's a lot easier to do, right? It's a lot faster. Okay, I think that's all I have to say for this video. Okay, yeah, that's it, guys. So I'll see you in the next one.